We are now going to explore the meaning of test response mapping and transformation set of functions. For this, we're going to use our previous example for estrogen binding mediated population reduction. And here we have one key event, which is vitellogenin messenger RNA induction in liver. And we have two different tests that are used as supporting evidences. One is the trout liver slices, and another one is part of the multi-generational MEDACA study. So this is the parent generation test, and you can see that those are the trout liver slices results for aminoaniline chemical, and here are the results for the actylphenol. But one thing that we have to note is that the chemical, in this case actylphenol, was actually supplied in the water, and the measured messenger RNA induction was a result of this in vivo experiment. But in order to compare those two tests, we have to both of them have to be converted to equivalent dose measures. So we need to have doses at the target site. So in the case of in vivo MEDACA study, we need to convert this water concentration to in vivo in liver concentration, and for that purpose kinetic study has been performed, which measured what is the steady state differences between this in vivo and in vitro concentration, and has established a bioconcentration factor of 160, and this allows us to use the measurements of the assay as they are and just transform the treatment levels so they are relevant to in vivo treatment levels. Now I'm going to show you how all of this can be done with our previous example. So again, we had those two key events here, and no transformation functions has been applied. But let's go here at the second one and create a new transformation set. New response transformation. And if you have noticed, the response of the in vivo test 3 was kind of 3 times bigger than the not 3 times, but 10 times bigger than the other test. So we can use that as something that we can scale. And the transformation sets could be more than one, because we can define different models. In the most complex case, we might need to supply the whole ADME model here, which transforms the availability of the chemical to the one that is relevant at the target site in vivo. But in this case, we're going to just define two simple functions. So I'm adding here at the transformation functions one function that is going to transform the response of the assay. So this is the assay measurement, and let's say we want to scale the response 10 times. So I can add a new proportional scaling function, which is a very easy to define. We just have one coefficient by which we multiply the input of the function. So let's define it like this. And here we have our test response is from 0 to 100, and then we can see that the in vivo response scaled by this response function is from 0 to 10. Let's also transform the statistical error So we are going to use exactly the same transformation type. Just make sure that we are transforming the error now. So let's add different function, and so let's go back to our diagram. You can now see that there is a symbol F, which denotes that we now have a transformation set defined. And if we go back to the response-response relationship, which was originally defined without using any transformation, so we can see that the key event 2, shown in green, is actually again 150. By the way, just to make it more easy to interpret, I'm going to change the name of the measured output here. So measured response to be key event 2 response. So if I go back here to the, we can see that this is the green one, is the key event 2 response. So let's now use our transformation function, which we defined. And you can see, because it's actually scaling our response of the in vivo test 3 assay to become in vivo relevant response. Now you can see that this is already in vivo response instead of the original not transformed one. And now if we derive, you can note that the old response-response relationship was kind of linear, but here we had from 0 to 20 and from 0 to 150, and if we regenerate it, it's almost linear one now. So this is the response-response curve after the transformation. So this is in principle how we can create how we can create transformation sets. I didn't cover many details, but in the future this will also become more flexible, so we can, instead of just using analytical functions here, we will be able to define external models which are going to predict or provide our transformations for all the data points here. Also, there is more information regarding each transformation set of functions that need to be entered in Effectopedia. Briefly, this is describing how biological context of your test assay is different from the in vivo one, and you also can mention these differences in terms of absorption, distribution, metabolism, and excretion terms. Also, you need to provide some information about the applicability domain of this transformation function. Sometimes the functions are derived for specific chemicals. Sometimes they are more universal, and you need to specify that.